invitation. I'm supposed to show this slide first, right? Thank you for having me here. I apologize to everyone who came only for Nessa. You'll have to suffer through my talk, and then you'll get her at another time, apparently. I'll talk today a bit about our work, and what happened was that when I was an undergrad, I remember thinking, why don't we chemists have statistic courses? And someone told me, well, we're a real science, so we don't need that, which is kind of ridiculous. And so more and more in recent years, you see statistical tools being used for chemistry. And I'll tell you a bit about what we've been doing with statistics in my group. And I call it statistics. Some people call it machine learning or artificial intelligence. It's all one big happy family. And I don't need to tell people these days why statistics are important, because we can see them in all of the analyses of what's going on with our lovely pandemic that we've been enjoying in recent years. And one of the things that was striking to me is how important statistics have become and how prevalent they've become in our daily lives, in the news. So for example, in Israel, in one of the newspapers, they have, and I'm assuming it's the same in the UK, they have the statistics of what's going on. And this is an example of why data analysis and visualization is really important. So here you can see a plot of the severely ill in Israel, of folks below 60 years old and above 60 years old. And you can see the numbers of unvaccinated people who got the second shot in Israel. We're already at our third shot because we started pretty early. And you can gain some insight from these types of plots. So you can see, for example, that unvaccinated are likely to catch a severe disease much more than those that are vaccinated. And that the third shot was apparently pretty impressively pretty good. And I was surprised by it, but it turns out now people have been doing some research and showing that it's really important to get it, especially if your second shot was given a while back. But if you compare these two, it's difficult to see, you know, with unless you have a keen eye and you love numbers and you're like, oh wait, this is 168 up here and this is 7.5. So yes, the portion of unvaccinated to vaccinated that are ill in both groups may be similar, the ratio that is, but if you look at the numbers here and here, you can see that above 60, there's a big difference, but this plot doesn't actually show it. And so in that same newspaper, they also show it in a different way that I think kind of highlights why data visualization, not only data analysis, but also data visualization can tell you something about what's going on. So these are called radial plots. And if you look here at a comparison between the all three groups at the below 60 age group and above 60 age group, you can see these huge differences where it leads you to understand how vulnerable people of above 60 are to this disease, because then you're really comparing the numbers that are down here with these numbers up here. And you can put all of this on the same plot. So there's a value to data visualization, which I hope to show you today with chemistry as well. Another, just an anecdotal point. So I keep showing these slides in the last few months. And so this is the slide from 1 month ago in Israel. And if you look at the slide from today that I took out from the newspaper, it looks pretty similar, right, in the ratios, but really here you have 60, you have 3.5, so we're in better shape here. So hopefully that things are looking brighter. There's something positive to say about this. So I'll talk now a bit about chemistry, not about COVID, hopefully. And one of the things that we've been doing in chemistry in recent years, and it's kind of the state of the art in optimizing reactions, is high throughput experimentation, where you take a bunch of catalysts and you take a bunch of conditions and you test them for a certain reaction, and you look for hits. So you can see the hits here in yellow, right? But what you also see in these high throughput analyses is that there are a lot of areas where you have this blue, the sea of blue, it's a sad sea of blue, of reactions that before people came in and did data analysis were considered bad results. These were going into the trash can of chemical knowledge, right? The only things that went into our chemical literature are these hints, things that actually worked. And then a bunch of smart people came in and said, oh, there's no such thing as bad results. There's only useful information about chemical reactions, because if you understand why these points are in blue, you understand why these intermediate points are in green, that they partially worked, then you can really understand why certain points are yellow and worked really, really well. And these smart people also said, okay, we can take these results and we can predict how reactions work. We can optimize them. We can also try to discover new reactions. And I think this is the state of the art of using big data analysis on high throughput stands today. So you can see some really nice papers coming out about that. And then a bunch of other smart people, some of them are the same smart people, said, you know, but we can automate a lot of this. And we can create these closed loop systems where a robot does these optimizations step by step, right? It takes the input from a high throughput analysis and sees, you know, what are the parameters that are optimal, and then moves to the next step. So you don't need humans involved in many of the steps of the system, and you see more and more people going towards these types of systems. But the interesting part for me, having a small group and you know, being interested in mechanisms always, is that within this automation, where's the human in the loop? Where can we find him? And one of the places, you know, I like anecdotes. I went to visit a company called ChemSpeed. They make these high throughput instruments, these big robots that, you know, sample different reactions and measure them, etc. And when we went to this back room in ChemSpeed, we saw these folks really focused and working on creating these instruments, like Swiss Watchmakers is a Swiss company. And I thought, oh, there's the human in the loop. But it's not only there, because if you look at the publications coming out about big data analysis, you see very nice visualizations. Now, the robots don't need these visualizations, right? They're fine, you know, just looking at the data. They're fine looking at ones and zeros. The human needs these data. They need the visualization. So that means that we all want, right? We want to keep the human in the loop. And one of the things that I will claim is that when you don't have a lot of data points, you can still use a lot of statistical or machine learning techniques to understand better your reactions. And our role in the loop becomes even more clear when we have very few results. And so, in my group, we don't yet have a high throughput instrument, though my students keep asking for a robot. So at some point, when we have the money, we'll probably get one. But for now, what we've been doing is we take our small-ish data sets. Well, when we think about big data, they're considered, our data sets are considered really, really small. And we create focused systematic libraries with the aim of doing a full data analysis, to uncover the underlying mechanism of the reaction, which is what interests us most, and discover new selective reactions, right? We want to understand why these areas are blue, these are green, and that will lead us to understand why these are yellow. And going back to this whole going back one slide, going back to this whole premise of, going from prediction to optimization to discovery using high throughput, people claimed that, we lose serendipity. And already in 2011, the Macmillan group, who are now of the Nobel fame, have shown that you can use high throughput to still get serendipitous results. They even called it accelerated serendipity. When I saw this initially, I was not bought. But now that there are so many high throughut kind of approaches, I think that this is kind of going back to this. It seems like a really smart thing that they did, because they say, you can embed serendipity in the process. You can try things that you have no idea whether they're going to work or not, and you can identify new reactions. But my claim is that even what we call serendipity here is confined to the chemical space that we've defined in the high throughput experiment, right? And things that are fully outside the box, such as for example, discovering penicillin because you forgot your petri dish and mold grew on it, that may be lost here. And so that brings me back to the point that small data analysis is really important as well. And that allows you to unleash your creativity and develop concepts that are fully outside the box. And with small data, I think I hope you'll see the human in the loop is crucial. And I hope to convince you that, dealing with small data, it's not just a necessity that comes out of the fact that we don't have high throughput yet, but it's key to bridging the gap between human and machine learning, because the understanding that you can gain from the small data can then be fed back into the loop of the big data analysis. All right. So I would say, in the world of small data sets, as you can imagine, it's all about the details. So now I'll tell you now you have heard me ramble on about data, but now you have to hear me ramble on about the details of our actual work in the lab. And so we work on organocatalysis, again, of recent fame. And it's, organocatalysis has huge potential because it's greener, less toxic, cheaper, and now people are really interested in it. The only problem is that when you dig into the details, organocatalysis often requires high catalyst loadings, there are issues with reproducibility, and it's tailored for a limited scope of substrates. And so in organocatalysis, similarly to catalysis in general, we've been learning from nature, and we've been taking the active site, say, of an enzyme and saying, okay, let's pluck this out of the enzyme, put it in a test tube and see how it works, which is extremely naive. And then in recent years, we've been learning from nature the hard way that, the actual environment in which this active site is embedded is critical, because this non-covalent environment really influences both the reactivity and the selectivity of the system. And so in organometallic catalysis, people have understood this. In enzymatic catalysis, people have understood this. And this is an example from Boronic and co-workers, where they put a second sphere coordination modifiers to direct the approach of a substrate into a catalytic site. But in organocatalysis, people don't really talk about secondary sphere interactions. So because in organometallics, you have the metal, you have the first sphere of ligands, and then the second sphere, it makes sense, it's the second sphere, it's not connected directly to the metal, but it's guiding the substrate. In organocatalysis, people think of the whole catalyst as some sort of secondary sphere phenomenon, which isn't fully true, because if you look at an organocatalyst, you have the area that is kind of the active site, the active catalyst, and then in its environment you can embed different things. And so people have been introducing, in organocatalysis, different groups that direct the non-covalent interactions of a substrate, and can introduce hydrogen bonding, the different pi interactions. But the limitation of this approach is that you have to synthesize each and every one of these catalysts to modify the interactions. And once you do that, oftentimes these catalysts are very specific to a certain substrate set. And so to circumvent these drawbacks, what we decided to do in my group is modify the catalyst while we do catalysis, which has its own challenges. But if it works, then you can add this secondary sphere modifier to your catalyst in the reaction mixture. And by doing so, you're in a position to introduce numerous interactions very easily. So far I've been showing just jigsaw puzzles. The way we have done this so far in the group is by using dynamic covalent bonds. And we did this by using boronic acids that combined to hydroxy and carboxylic acid groups, which are prevalent in organocatalysis. And we like to use boronic acids because they're they're just everywhere. Not because of us, because some unknown coupling Suzuki type reaction. But what you can do with these, because they're so prevalent, is that you can buy any structure you want. You can make many of these, and you can modify the location of your substituents. You can modify their size. You can modify their electronic properties. And what this allows us to do as people who want to build small data sets is modify our catalysts very easily. Now, in order to showcase this approach, we were looking for a reaction where we knew that reactivity and selectivity can be tuned by non-covalent interactions. And a reaction we came upon was the benzoin coupling. We thought, this is a reaction that has been known for many, many years. So we surely be able to, use everything that's known about the mechanism of the reaction. Then it turned out that the mechanism was not that well known, but still it was a good choice in hindsight. So this reaction takes an aldehyde and it binds to it. The catalyst binds to it, the carbene catalyst, and does an ompolon to reverse the polarity. And this new species called the Breslau intermediate can then attack a second aldehyde and form this benzoin product. And the other thing that attracted us to the system is that the catalyst had been used, and the best one for the system until that point had a hydroxy group in it. So we knew that we could modify sterics and electronics in our catalyst library, but we could also modify the in situ non-covalent environment by adding a boronic acid under reaction conditions and get our small library of catalysts with very little synthetic effort. Now, we needed a reaction where there was some limitation to show the usefulness of our method. And we found that, if you read the fine details of the literature, you see that even the homocoupling reactions, benzoin reactions, have a low enantiomer selectivity for electron withdrawing groups, likely due to a racemization that happens to the product. And there were a lot of reproducibility issues with the optimal system. You read the SIs of the papers, you kind of feel the tears of the students. Like, I tried to reproduce this and it didn't work, and even in our results you can see this. So we took a set of electron withdrawing substituents on aldehydes, and we ran them with and without boronic acid. So without boronic acids you see them in gray, and with boronic acid you see them in blue. And so we were happy to see that not only were we getting higher enantiomer selectivities, but we were also getting much more reproducibility. So some of these reactions really have a huge error bar. But all of this is to show you what we do with data analysis in these types of systems. So what we tried to do at this point is we first had a set of different aldehydes with one type of boronic acid. So since we keep the conditions constant, we could produce a model that describes the changes to the aldehyde, because it's the only part of the reaction that is actually changing. And so we try to use well-known parameters to describe these aldehydes. One of them is are the stereomole parameters, which are steric parameters. So this is L, the length of the substituent. This is B5, the maximal width of the substituent. We tried to look at charges at different points on the aldehyde, and we tried to look at vibrations, but none of these really worked well to describe the molecule. It was only when we introduced the directional components of the dipole moment that we were able to get a model. And these are parameters that people hadn't used before. They were there. So if you look at any computation that comes out of DFT, you have the directional components of the dipole moment. Though the thing is that the dipole moment is normally not located in one point on the molecule. So you have to make sure that your axes start from the same origin. And then you can look at these directional components of the dipole moments across a set of molecules. By doing that, we were in the position to describe all of our aldehydes using three parameters. It was the length of the aldehyde, its maximal width, and the component of the dipole moment on the axis of this length. And so we get a great model. It's fantastic. It's a really robust model. It is cross-validated, meaning you can take some of the results out and predict them with the other results. But the problem is that we now end up with an equation with three parameters. So on a good day, I can, intuitively look at two parameters and kind of say what the next substrate may look like. And that's on a really good day, because normally it's easiest just to look at two parameters. Once you have more, one parameter, a univariate correlation. Once you have more, it becomes kind of difficult. And then with three parameters, you kind of lose a sense of what's going on. So this is a normalized model. So one thing you can say about it is that there's a minus sign before all of these parameters. So you can for sure say that the enantiomer selectivity here represented by delta delta G, which is an energy that represents selectivity, is inversely correlated to all three, meaning that the wider your molecule, the longer your molecule, the stronger the dipole moment in this direction, the lower your enantiomer selectivity. Fine, that's all great. But how do I know if the next molecule is going to have higher or lower enantiomer selectivity? Because all of these three are kind of competing with each other. So I don't really know. I won't really know. So that's where data visualization can come into play. Here you can see in the diamonds the delta delta G, so the enantiomer selectivity. And here in the colorful bars, you can see the contribution of each of these parameters to the model that predicts the delta delta G. So again, you can see that if you have more of orange, so wider molecule, more of L, longer molecule, more of UL, so stronger dipole moment, the lower your enantiomer selectivity is. But what it also reveals are things like these, where you can see here two substrates that normally in any mechanistic work, people would say, these get the same enantiomer selectivity under the same reaction conditions, they probably work the same. However, if this model is telling us anything about reality, then the reason that these have this specific enantiomer selectivity, which is kind of lower than you'd expect, is different. Right? This is all blue, giving us the lower enantiomer selectivity, and this is all orange. And so we wanted to probe whether we could use this visualization to really fine-tune our conditions for different substrates, because oftentimes in the industry, they're not interested in the whole scope. They have one substrate that they want to deal with. And so the first thing we wanted to look at was this mu component. We thought this could have to do, a strong dipole moment in this direction could have to do with the racemization, right? If we pull in this direction, it's easier to racemize here through a keteroenol type mechanism and under basic conditions. So we said, you know, maybe if we add acid to these reactions, we'll be able to circumvent that. And so we added acid, and indeed, in this case, we had a bump up in enantiomer selectivity, which was fantastic. But here, nothing had changed. So this really shows that you can really fine-tune the enantiomer selectivity here. And then we said, okay, so what is B5? What is B5 signifying? And we knew that when you put the substrate in a Breslau type intermediate, there is some pi type interaction with this ring here on the catalyst. And we didn't know what type of pi interaction, but we did know that any pi interaction, if you change these fluorines to hydrogens, then you'd get a very different interaction. And so we did that, and by taking this different catalyst, we were able to bump up this enantiomer selectivity, but this one was unchanged under these conditions. So really here, by analyzing, by visualizing the data here, we were able to produce the conditions for fine-tuning this reaction. Now, to this point, I didn't tell you about the role of the boronic acids, and again, even in this work, we weren't certain what exactly it was doing. We are now doing computations, and it's doing some crazy things. So hopefully soon you'll be able to see it. But the one thing I can tell you is that when we tried to correlate the results, the reaction with one aldehyde and different boronic acids, we could not get a linear correlation. And what this indicated to us is that there wasn't really a linear relationship between our outcome, the enantiomer selectivity of the product, and the R group on the boronic acid. And this is because we were looking at two reactions. We were looking at the benzoin reaction, the forward reaction, as well as the racemization reaction. So we couldn't get a linear correlation, but what we could do is we could build a decision tree around the different boronic acids. And what a decision tree does is classify the characteristics of these boronic acids into groupings based on their characteristics. And so, for example, here, if you look at the torsion angle between the boronic acid moiety and the ring moiety, you see that if you have torsions that are larger than 40, the angle is larger than 40, then you get pretty low enantiomer selectivities. This is in delta delta G again. And so we assume that this is because when you have this high torsion angle, the binding of the boronic acid here would be lower. And then we added different, dipole moments, etc. And you can classify all of the different boronic acids based on these characteristics. So you have this grouping here, which gives you the highest enantiomer selectivity. So you have a low torsion angle, you have high dipole moment in this direction, high dipole moment in this L direction, and that leads you to the highest grouping. But it also led us to find these different groupings here of boronic acids that give varied predictions of the enantiomer selectivity. So this is all fine. We cannot do much with it, but we thought what we could do with it is having had this information in hand, maybe we can use it to do a really fast optimization. And so what I'm going to show you now is an optimization from 6 small % of catalyst, which, as I told you, was one of the problems in organocatalysis is the high loadings, So we wanted to drop the catalyst loadings to 0.1 mol%. And I'm going to show you an optimization to 0.1 mol% that we did within 1 week. And so normally it takes a while to do these types of optimizations, but having used the tree that we had before, we were able to really streamline it. And so here we take 0.1 mol% of catalyst, and we take kind of a bit of base, and we run the reaction on gram scale. And taking our best conditions, we used the 4CF3 boronic acid, and we got the same enantiomer selectivity that we'd seen before, but the problem was that we were getting really low yields, which again is something that you see when you scale down, when you scale up a reaction and lower your catalyst loadings, which we did all at the same time. So we said, maybe electron withdrawing groups on these boronic acids somehow slow down our reactions. So this was where intuition, the human in the loop, meets data analysis, because we had this tree here that we could use to probe this. So we said, if we look down here, we see enantiomer selectivities that are not that far from the highest ones. And we have electron donating groups here. So maybe if we try an electron donating group boronic acid, we'd be able to get higher yields, but still retain our high enantiomer selectivity. And so in our first trial of using one of these boronic acids, so 4-methyl that is electron donating, we are able to bump up our yield to 60% while keeping our 95% EE, which was fantastic. And this is, again, a combination of intuition and statistical techniques. And then we said, and the reason we don't get any loss of EE is that the catalyst and the base here are in very low loading. And so the racemization that we saw here doesn't really harm our enantiomer selectivity. And so the next step was saying, okay, so I guess that pushing electrons into the boronic acid is beneficial for our yields. So I'll look for another substrate here that may help me. And looking here, I see that 2-methyl doesn't really change, the width or the dipole moment or the torsion, etc. So maybe if I take 2,4-methyl, I'll get the yield that I need. And indeed, at the end of the week, we're already with 90% yield and 95% EE for this reaction, which shows you that these types of analyses, as uneventful, right, that they may be when you just get them, can be very, very useful in optimizations. And so we were still wondering what the role of boronic acid is, but we found that that one of the roles for sure is that it stabilizes our reactive intermediates. So Zaid, who's here on the paper, is a very lucky guy. He thought that, if the boronic acid really stabilizes our reaction intermediates, he'd be able to see it by mass spec. I didn't think so because, for example, the Breslau intermediate, and this is the acyl anion, the Breslau intermediate was known since Breslau suggested it in 1958 and was only identified in 2012. So these intermediates are pretty transient and difficult to kind of catch. But he's so lucky. And so he managed to get mass spec of something that may look like this compound, so an acyl anion that is stabilized by boronic acids, showing that one of the roles indeed of boronic acid is stabilizing our intermediates. And this led us to our next project, which was, we can use maybe the boronic acid to stabilize our reactive intermediates, right here, for example, or we can use just NHCs that really have stable reactive intermediates and don't really engage in benzoin coupling reactions. And if we manage to block this path, we would be able potentially to kind of boomerang the aldehyde back, and by using D2O, get it to deuterate. Now this was because it was we had to deuterate some of our products to do a crossover experiment in the previous project, and we knew that getting deuterated aldehydes has been a pain because you need to use different reagents, low temperatures, etc. So if we could, use this reaction pathway to actually get deuterated aldehydes in this very mild way, it would be great. And we kind of presumed that this would be some sort of proposed mechanism for this reaction. So going to the Breslau intermediate, then attacking water and getting the product. And we knew that, so this is work in 2012 where Berkesel and co-workers were able to see for the first time Breslau intermediates. So we knew these kinds of NHCs, cyper, cymers, were very stabilizing and wouldn't likely lead to benzoin products. And then we also knew that when you have two substituted aldehydes, you get pretty stabilized acyl anions using the triazole catalysts. So we used these systems as a starting point, and we used cyper to kind of get gauge where we were in terms of the problem at hand. So we took a regular, benzaldehyde with no substituents on it and submitted it to reaction conditions where we had cyper, D2O, and the cyper was at 5 mol% and base at 5 mol% to see if we get deuteration. So the deuteration here is in blue and we get full deuteration, but we also get the benzoin product, which is problem. Then if we go to the two substituted aldehydes that we know lead to pretty stable acyl anions, we don't get a fully deuterated product, right? But we don't get any benzoin. One solved issue from the get-go is these electron donating type groups that are fully deuterated and you don't get any benzoin product. But then if you go to electron withdrawing groups, you get fully deuterated product, but you also get a hell of a lot of benzoin product. And so these were the problems we had to face with this system. So we decided to start with these two substituted aldehydes. And the first thing we looked at was the rate of reaction for different aldehydes. So you have the rate here in gray, and for people who love physical or organic chemistry, you have log of the rate up here. It's basically the same idea. So the rate goes down and you cannot really see a good trend in terms of sterics or electronics. So we said, okay, so let's model these results and see if we can get parameters to tell us what's going on here. And what the parameters told us, so we got a really nice correlation for the rates of the reaction. And we got two parameters in the model, the B1, the minimal width of the substrate, which is actually its thickness, and the dipole moment in the direction of the substituent. So what this model is essentially telling us is what our intuition was telling us to begin with, and that is that both sterics and electronics influence this reaction. Fantastic. That doesn't give us much. But what it did allow us to do is say, so if we need a new catalyst that can deuterate aldehydes that are with substituents at the 2 position, we would need catalysts that vary in terms of sterics and electronics. We would need at least to probe those. And so we designed a data set of triazoles where we varied the aryl group here. And we changed both sterics and electronics. And eventually you see that the one that comes into play has really characteristics that change it in terms of both sterics and electronics. So this pentafluoro is still in the same plane as the triazole, whereas once you have 2,6 bromine on your aryl ring, it's going to be more perpendicular. And so both sterics and electronics influence this reaction. Then, we already had this data, so we said, okay, let's model it. And by just taking the catalyst, we weren't able to get a correlation. But then going back to our proposed mechanism, we said, we have to go through oh, this should have been the previous slide. We should go through our Breslow intermediate. So we took the Breslow intermediate, and by taking the Breslow intermediate, we were able to get a good correlation. And the correlation has two parameters. It's the delta in charge between the carbon on the carbene and its proton in the pre-catalyst, and the two carbons, one on the attached aldehyde in the Breslow intermediate and the carbon. And what we also noted was that we were getting a good correlation with the E isomer, but not with the Z isomer. And that was leading us to kind of an assumption that it is the E isomer that is active in our mechanism. And then from computations that we did on an unrelated project, we noticed that, yes, it is indeed the E that gives the lower energy enantiomer, and that's probably the one that is reacting. And so now with these in hand, we wanted to go to the to solve our problem. So I'm running a bit over time, but I promise you I will be done within 5 minutes, so please bear with me. I told you earlier, this was a solved case. So we had a scope where we were able to deuterate a bunch of substrates. This is a radial scope where each of these slices represents one substrate. You can see here in red the yields, and you can see in green the percent of deuteration. So really nice results because we were fully able to use these conditions to suppress the formation of benzoin. Now, for the substrates where we were getting a lot of benzoin product that had electron withdrawing groups, I told you there was a preamble for this, that boronic acids could potentially give us a more stable intermediate that would suppress the formation of benzoin. And so for these types of substrates, indeed, the only thing we needed to do was add to these reaction conditions a catalytic amount of boronic acid, and we were able to get a bunch of other substrates to undergo the reaction. And finally, the ones with the substituents at the 2 position that were not really undergoing full deuteration with the cyper, we got to fully deuterate with these triazolium catalysts. So, and we had a few outliers. And so if I'm telling you about these outliers, then it means that there is maybe going to be a model in a moment. But these outliers were experimental outliers. So these two required a different solvent. And this one required an equivalent of boronic acid to not provide any of the benzoin product. So these were left out in our model. But what is this model? So the model is what we call an enhanced scope. So wouldn't it be nice if you have a scope of a reaction, if someone told you, if you come in with a new substrate, which conditions should you be using? Because we showed 3 different conditions which we selected specifically so that we wouldn't have many. So, but if you look at deuteration papers especially, but many different papers, you have specific catalysts or solvents or temperatures for different substrates that were optimized individually. And here we had 3 conditions, and we wanted to show people if you have a new substrate, which condition should you choose? And what we did was we did a classification model where we take each of these conditions. So this is cyper and boronic acid, this is cyper alone, and this is triazolium. And we try to see whether or not we can use parameters to predict the condition to use with each substrate. And this matrix here is called a confusion matrix. It is because it's confusing, but in essence, you only need to look at this diagonal, which tells you how accurately we can predict each of these classes. So with cyper and boronic acid, we basically managed to predict all of the substrates accurately in terms of whether you should use cyper and boronic acid or these 2 other conditions. And we predict cyper pretty accurately. And then for the triazolium, it's slightly lower because we have a smaller subset requiring these conditions, but still it's not too bad, 7 to 3. And the overall accuracy is almost 91%, which is pretty good. What does this mean? So we get this table that's showing us the probability that these are the right conditions for us. So if you take this substrate, let's say 2-fluoro-benzaldehyde, the model is telling you with 54% probability, these are the best conditions for you. So it's not very accurate. So you don't really know if you have 2-fluoro, maybe we should use this condition, maybe it won't work. But for example, for the 4-cyano, you know that this is probably going to be the right condition because it's predicted at 100% probability. The parameters that are used for this are very simple: the maximal width of the aldehyde, the length of the aldehyde, and the vibration of the CO stretch, as well as the difference in charge between the C and the O. And so this is for cyper and boronic acid. These are the probabilities for using cyper alone. So here it misses twice and predicts, instead of predicting cyper alone, here for 2-methoxy, it predicts the triazolium, and here for 2-CF3, it predicts cyper and boronic acid. But interestingly, these two actually required higher levels of base. So the model is telling us something about reality. So in all of the cases, we used 5%, 5 more percent of base. Here, 5 more percent of base didn't give us full deuteration and full suppression of the benzoin product. So we used 10 more percent. And so the model is kind of onto something. With that, I'll end just by saying my general message is by by using data analysis, machine learning, statistics, even for small data sets, it really enables you and is an exquisite playing ground for new ideas, features, concepts, and it allows you to unleash your creativity in chemistry. And so I will thank my group that were the actual heroes in the story. Shachar and Inbal did a lot of the classification work. 2 postdocs that, I erased their names here. So Dayalan Vasudevan and Santosh Gadekar, who did a lot of the benzoin work together with Zaid Al-Assad, who is now finishing his PhD in my group. The 2 of them, one of them has a new position and the other is a Curie Fellow at ICIQ in Spain. That's it. With that, I'll thank you and all of our collaborators and funding agencies. Thanks.